How about one of you telling me what you're doing with your head buried in that 4-speed gearbox?
Oh, hello, Tech. I was just about to give Joe here a quick lesson on the 4-speed manual transmission. Why don't you stick around and lend a hand?
Suits me just fine, Bill. How do you propose to start this lesson?
Unless you have a better idea, I thought I'd start with a review of the power flow in each gear range, then cover the shift linkage adjustments, and finish up with some of the latest service tips.
That sounds good to me, Bill. You know, Joe, if you have a clear idea of which gears and parts are involved in each gear range, you'll do a better job of diagnosing shifting and operating problems.
I have a general idea of how a manual transmission works, but I'm anxious to learn exactly what goes on inside this 4-speed job.
Okay, Joe. I'll do my best to explain what the gears in this box do. I think the best way to start is to identify the main parts of the transmission. To simplify things, let's break these gears down into 3 major groups, or sub-assemblies. The main drive pinion is at the front end. Behind that is the main shaft assembly with its gears and synchronizers. Below this is the cluster or countershaft gear. Now let's see what they do. In 4th gear, the drive pinion is coupled directly to the main shaft. Power comes in through the pinion and goes out through the main shaft without any change in speed or torque. That's why it's sometimes called direct drive. Now here's a most important fact to remember. In all ranges except 4th gear, there is no direct mechanical connection or coupling between the drive pinion and the main shaft. Here's why. The front end of the main shaft is piloted or supported in roller bearings at the rear end of the pinion gear. So, the pinion and main shaft are free to turn independently except when they are coupled in 4th gear.
In neutral, the gears on the main shaft are free to turn. In other words, they're not coupled or mechanically connected to the main shaft. The 2 synchronizer assemblies are always mechanically connected to the main shaft. That's because they are splined to the main shaft. However, the clutch sleeves can slide back and forth.
The important thing to remember is that the synchronizer assemblies are always coupled to the main shaft. Now let's tackle the power flow. The drive pinion is always meshed with a cluster gear. So, anytime the pinion is turning, it turns the cluster gear.
And that means the gears on the main shaft turn too. But they don't transmit any power in neutral or 4th, right?
Exactly, Joe. However, when you shift into low, the 1-2 clutch sleeve couples the 1st speed gear to the main shaft. The power flow is from pinion to cluster gear, from cluster gear to 1st speed gear, and then out through the main shaft. When you shift into 2nd, you simply move the 1-2 clutch sleeve forward. The clutch sleeve couples the 2nd speed gear to the main shaft. The power flow in 2nd is from the pinion gear to the cluster gear, then from the cluster gear to the 2nd speed gear and out through the main shaft. The 3-4 clutch sleeve does the coupling and uncoupling for 3rd and 4th gears. The 1-2 clutch sleeve stays in neutral.
As a matter of fact, whenever one clutch sleeve is engaged or coupled, the other one has to be in neutral. Otherwise, you'd be in 2 speeds at the same time and tear up some gear teeth. But more about that after Bill finishes explaining power flow.
In 3rd, the 3-4 clutch sleeve couples the 3rd speed gear to the main shaft. The power flow is pinion gear to cluster gear and 3rd speed gear to main shaft. Of course, the 1-2 clutch sleeve stays in neutral. As we said earlier, in 4th, the front clutch simply couples the main shaft to the pinion gear, and the power flow is straight through the transmission.
In other words, the cluster gear is turning, but it's just going along for the ride, without transmitting any power. Now how about explaining power flow in reverse?
As you can see, the reverse idler is a spur gear, Joe. The only time it turns is when you shift into reverse. That's a feature of our transmission. The reverse idler is a sliding gear. It meshes with the spur gear teeth on the clutch sleeve and the spur gear teeth on the cluster gear. To shift into reverse, you slide the reverse idler into mesh with the teeth on the clutch sleeve and the teeth on the cluster gear.
I can see what happens when the reverse idler's engaged. The engine's turning the pinion gear clockwise. That means the cluster gear's turning counterclockwise. Since the cluster gear's turning counterclockwise, it's driving the reverse idler clockwise. That means the main shaft has to be turning counterclockwise. So, the car backs up.
You sound like your needle's stuck, Joe. But I gotta admit, you got all your clocks and counters straight. Do you have any questions on power flow in this 4-speed box?
No, but I would like an explanation of how the synchronizers work.
As you know, there are 2 synchronizer assemblies. Each assembly includes all the synchronizer parts. Since all the synchronizers work the same way, we'll only have to explain one of them to begin with. Let's get acquainted with the main parts of the synchronizer assembly. There's a stop ring, a clutch gear, shift plates, and the clutch gear sleeve. Let's see how they fit together. The splined clutch sleeve slides over the external splines of the clutch gear. When the sleeve and gear are fully assembled, you can just see the ends of the 3 shift plates. Next comes the stop ring. You'll notice there are 3 notches in the stop ring that match up with the ends of the 3 shift plates. These notches are wider than the shift plates. We'll explain why in a minute or two. First, let's see how this looks in a sectional drawing. Each shift plate has a ridge across its middle, which fits into an internal groove machined into the clutch sleeve. This is a detent arrangement to hold the plates in position in the sleeve, so they move back and forth with the clutch sleeve. Now let's put the whole synchronizer assembly on the main shaft. The clutch gear has internal splines which key it to the splines on the main shaft. A snap ring locks the clutch gear in place on the main shaft. Any questions, Joe?
I've got several, Bill. But maybe if you'd explain exactly how the stop ring and those other parts synchronize a shift, that would answer all my questions.
Okay, Joe. Here's what happens on a shift into 4th. In order to get into 4th, we have to slide the clutch sleeve over the teeth on the main drive pinion. Of course, the pinion gear and the clutch sleeve are turning at different speeds. When the driver starts to shift, the stop ring is pushed toward the cone-shaped shoulder of the drive pinion. The inner surface of the stop ring is cone-shaped too.
It works something like a cone-type clutch, I suppose.
Correct, my boy. Of course, it's the ends of the shift plates pushing on the stop ring that actually move the stop ring into contact with the cone on the pinion gear. But I better let Bill tell you about that.
As soon as the stop ring is pushed against the cone on the pinion, friction tries to make the stop ring rotate at the same speed as the pinion. Actually, it does rotate until it's stopped by the shift plate. The shift plate positions the stop ring so that the ends of the internal teeth of the sleeve push directly against the stop ring teeth.
The stop ring momentarily blocks the shift if there's quite a difference in speed between the pinion gear and the clutch sleeve. That's why it's called a stop ring. Of course, since the sleeve's pushing the stop ring against the cone of the pinion, friction soon makes the pinion start turning the same speed as the sleeve.
When everything's turning the same speed, there isn't much torque load on the stop ring. So here's what happens. The chamfered ends of the sleeve teeth nudge the chamfered ends of the stop ring teeth sidewise, and the ring rotates slightly. This lines up the teeth so the sleeve can slip past the stop ring teeth. To complete the shift, the sleeve slips over the teeth on the pinion. This couples the pinion to the main shaft. Any questions?
Just one. Who's gonna turn the record over?
That gives me a good understanding of power flow and the synchronizers. Now, how about explaining the fine points of the shift mechanism?
Glad to, Joe. As you can see, the 3-4 and the 1-2 shifter shafts are part of the cover assembly. There's an interlock mechanism between the 2 shifter shafts.
That interlock keeps the 3-4 shifter shaft from moving when the 1-2 shifter shaft's not in neutral and vice versa. In other words, you can't shift into 2 forward gears at the same time. Now here's a tip. Don't leave the detent ball pin out of the interlock when you build up a cover. If you do, the detents will work all right, but the interlock won't. I've seen fellas lose that pin and never even miss it.
I'll watch that, Tech. Now maybe one of you can tell me what this cam-shaped extension on the reverse lever is for. I can see how the reverse lever moves the reverse idler gear, but that cam stumps me.
That cam prevents an accidental shift into reverse when the transmission's already in first or second. It does a couple of other important things that Bill will tell you about.
Let's suppose the transmission's already in first. The cam on the reverse shifter won't let you shift into reverse while you're in first because it would hit the 1-2 shifter cam. Likewise, when the transmission's in second, you can't shift into reverse because of interference between the reverse shifter and the 1-2 shifter. Now, let's look at another possibility. Suppose that when shifting into reverse, the teeth on the reverse idler gear butted head-on into the ends of the spur gear teeth on the clutch sleeve. This could bump the sleeve rearward, right into first at the same time you were shifting into reverse.
Of course, you know what would happen if you let out the clutch when the transmission was in both reverse and first. Explain how that cam on the reverse shifter keeps that from happening, Bill.
Okay, Tech. On a shift into reverse, that cam on the reverse shifter slides into contact with a cam-like surface on the 1-2 shifter before the reverse idler gear gets close enough to mesh with the teeth on the clutch sleeve.
In other words, the close fit between the cam surfaces of the 1-2 and reverse shifters keeps the shift fork from moving. This in turn keeps the clutch sleeve from moving and being accidentally bumped into first gear. That close fit does something else important. Once you complete the shift into reverse, the fit between those two cam surfaces holds the 1-2 clutch sleeve exactly in neutral. That means the sleeve can't shift slightly, cause a stop ring to drag and wear out. You better tell Joe how to adjust the cover to get the cam surfaces just right.
Assemble the cover. Its formal name is gear shift control housing, with the 1-2 and the 3-4 levers in neutral. Put the reverse lever in reverse. The attaching bolts should be just barely snug, so the cover can be shifted by tapping it. Tap the cover downward toward the reverse lever to make sure the cam surfaces of the 1-2 and the reverse shifters are contacting each other. This will give you a pretty good initial adjustment of the cover. To check the adjustment, remove the reverse detent plug so that the detent doesn't hold the reverse shifter in position.
Don't accidentally unscrew the detent spring retainer, or the detent ball will drop into the transmission.
Good advice, Tech. With detent plug removed, move the reverse shift lever an inch or so in each direction. You should feel a definite drag between the reverse and 1-2 levers. Finally, move the reverse lever into the neutral position. Then, test reverse lever travel from neutral to reverse. You should feel a slight drag as the reverse and 1-2 shifter cam surfaces meet. However, the fit must not be so tight that the reverse shifter is blocked out of reverse. If it is, you'll have to reposition the cover slightly.
Here's something to remember, Joe. The 1-2 shifters are a selective fit. If you ever replace a 1-2 shifter shaft, be sure and get the right one. Or if you install a new cover, you may have to put in a new 1-2 shifter. Here's why. Shifters are marked A, B, or C. The shaft-to-cam surface distance of a B shifter is greater than an A shifter. On a shifter marked C, the distance is still greater.
I get the idea. If an A shifter's too loose, try a B shifter. Or maybe if a C shifter blocks the shift into reverse, it's too tight, and you should try a B or maybe an A shifter.
That's the ticket, Joe. Now for shift linkage adjustments. It's impossible to overemphasize the importance of correct shift linkage adjustment. Everything in the linkage must be right on the button.
Why is that?
Remember, if one of those clutch sleeves moves more than about a 1/16 of an inch, it'll push a stop ring against the cone surface of a gear. If shift linkage is off very much, a stop ring will drag and wear out pretty fast.
Another thing. It doesn't take much misadjustment of the shift rods to cause a rough crossover condition and poor shift quality. Bill will tell you how to go about adjusting the shift linkage to get easy shifting and good shift quality.
I start with all 3 rods disconnected from levers at the transmission and put the 3 shift levers in neutral. Then, back off both the front and rear shift stop screws. You'll find out why we do that a bit later. Install this special tool to hold the 3 levers in the shift assembly in neutral.
Be sure and use that tool. Don't try and line those levers up by eyeballing them.
Good advice, Tech. Adjust each rod as carefully and accurately as possible. Turn the shift rod or swivel until the effective length is exactly right, so you can slip it into the hole in the shift lever without moving the lever even slightly out of its neutral detent position. Remove the aligning tool and double-check the accuracy of the adjustment by testing shift lever operation through all gear changes.
Most important, move the lever through the gates several times to test for smooth crossover operation. There should be no roughness or bumping going from 3-4 to 1-2 and through the reverse gates or coming out of reverse into the 1-2 range.
But how could the crossover be off if you use the tool?
Here's why, Joe. You have to adjust each rod 1 full turn, but sometimes 1 half turn gives you correct rod length. In that case, you have to turn it another half so you can assemble it to its lever. If you guess wrong on that extra half turn, you may have to readjust to get rid of crossover bump.
Here's a tip, Joe. Make sure the crossover between reverse and the 1-2 range is smooth going in both directions through the gate. If it isn't, I found that a 1-turn readjustment of the reverse rod will usually clean it up.
I'll remember that, Bill. Now how about those stop screws we left loose?
Don't adjust those stop screws until after you've adjusted the rods. Then with the shift lever in 4th, turn the front stop screw in by hand until it just touches the lever. Back off 1 half turn and lock up the adjustment with a lock nut. Adjust the rear stop screw with shift lever in 3rd. Turn the screw in until it touches, and then back it off 1 half turn.
What do those stop screws do?
Those stop screws keep hot rodders and speed shifters from slamming the shift lever too far and bending the shift rods, or maybe cracking the shift cover. Actually, those stop screws aren't too important on normal, sensible shifts. However, here's something that is very important. Make sure the stop screws are not turned in too far. If they are, they can prevent full transmission clutch sleeve engagement. Partial engagement causes jumping out of gear and can cause gear damage. Wow, I don't know where the time went, but we better wind this session up by telling Joe about some of the additional information in the reference book.
Okay, Tech. An oil slinger must be used with early production pinion gears. Present production pinion gears have a wider boss and don't use a slinger. You'll find the details on this in the reference book. There's a new 1-2 shift fork that goes halfway around the clutch sleeve. If you have a shift problem that can't be cleared up by correct linkage adjustment, it's a good idea to try a new fork instead of dropping the transmission out of the car. Now, this isn't a nuts and bolts session, but you'll find some real practical service tips that'll help you do a better job of servicing this transmission. For instance, let me tell you about this homemade tool. Unless you happen to have 3 hands, compressing the center bearing snap ring with a pair of pliers while you try to separate the main shaft assembly from the extension housing is a mighty unhandy proposition. I formed the end of this piece of copper tubing into a rectangular shape so that it just fits over and holds the tangs of the center bearing snap ring together.
You'll find out how to make and use that handy-dandy snap ring tool if you read the reference book. As a matter of fact, the reference book for this session covers everything we've talked about today and a lot more besides. Be sure and read it and keep it handy. If you do that, you'll be prepared to handle the next 4 on-the-floor service job that comes your way. Customer car care is always important, and sometimes kind of interesting. See you all next month. winding up another successful model year. And we at Chrysler couldn't be happier about the way the public has gone after our 65s. In fact, 1965 sales have set a new corporation record. And why not? We have great cars, and our salesmen have really put them across. We're sure they'll even do better in 66. As master technicians, our part of the 1965 story still has a long way to go. 2, 3, or even 4 years from now, our 65 customers will be coming back to us for the best in service. So it's up to us to take good care of these 65 models. And to make our job easier, we have to keep up to date on all the service procedures, design changes, and modifications. Well, with that in mind, let's sashay over where Pete and Gene are talking and do a little brain picking. Howdy, gents. What's the good word?
Well, hi, Tech. Gene and I were just kicking around some of the latest service bulletins.
Glad to see you're keeping well informed. How about passing on some of your tips to all the technicians?
Always happy to oblige, Tech, but I think I'll let Gene hit some of the torque flight changes first. Okay, Gene?
Right, Pete. We've had a few important running changes. One mid-year change in the A727B torque flight smooths out the shift from neutral to drive. It's a new rear clutch assembly that cushions the clutch application. A wave spring and a spacer were added between the bell bill washer and the clutch pack to provide a more gradual application of the clutch. There's also a new clutch retainer, clutch discs, and pressure plate. With these new parts, the clutch pack clearance has been increased to between 37 and 60 thousandths of an inch. Another mid-year improvement was a new rear annulus gear support and the addition of a hardened thrust plate. The thrust plate is splined to the output shaft between the annulus support and the reverse planet pinion carrier. With a new annulus support and thrust plate, the rear planetary set runs a lot smoother and quieter.
Speaking of clutches, I'd like to talk about some of the reported clutch failures that turned out to be caused by something entirely different. For instance, an incorrectly adjusted throttle linkage or low oil level can cause low throttle pressure, which in turn will result in a delayed or slowed clutch application.
You can get the same condition if the gear shift control cable to the manual valve is not correctly adjusted.
You sure can, Gene. And either way, it means eventual clutch burning.
By the way, Gene, did you ever find out what causes that noise when a torque flight job's backing up?
I sure did, Pete. Here's the story. When the transmission is cold, the oil level is slightly lower than normal, so there is some aeration in the oil. When the bubbles reach the outlet portion of the pump, the outer pump rotor is forced away from the pump housing momentarily. The noise is created by the rotor oscillating in the housing. The oscillation doesn't harm the transmission in any way, so since it happens only in reverse and only when the transmission is cold, it's simply a matter of explaining the noise to the customer.
That's real important, Gene. Once you convince the owner that the noise won't hurt anything, he'll probably ignore it from then on. What's next?
Well, I'd like to talk about variable speed wipers on Furies, Poleras, Chryslers, and Imperials. One of the problems on some early production cars was loss of the shunt circuit ground at the wiper switch. Now, without a shunt circuit, the wiper motor overspeeds. And worse than that, you can burn out the motor. So, don't make the mistake of just changing a burned-out motor. Check out the switch and wiring to find out what caused it.
There's a good explanation of why the motor burns out in the reference book. Now, how about that switch checkout, Pete?
The switch problem has been corrected in production. A new switch with a longer grounding tab riveted to the switch case provides a more solid ground. To check the switch circuit, disconnect the motor connector and hook a jumper between the blue and black switch leads. Run a test light between the red and yellow switch leads, and then turn the ignition switch to accessory with the wiper switch off. If the test lamp lights, the wiper switch and wiring to the connector are all right. If the switch checks out okay, ground either the red or yellow motor lead and connect a test light between the other lead and the positive battery terminal. If the lamp doesn't light, there's an open in the motor shunt circuit.
Before you replace the motor, though, use a test light or an ohmmeter to check the connector and the wires to the motor.
Right, Tech. Another wiper problem on Furies, Poleras, and Chryslers is caused by incorrect installation of the wiper arms on the pivots. There's a special tool for removing and installing the arms. Tool number C3982 releases the spring tension that holds the arm on the pivot. Now, if you try to use any other tool, you're liable to distort the retaining clip and ruin the arm. Examine the serrations on the pivot and inside the socket of the arm for distortion. Also, make sure the arm retaining clip is not bent or loose.
Here's another tip on wiper service. When you're putting a blade on the arm, it's possible to get it on too far. To avoid this, push the blade on the arm until you hear it snap into place. Don't press the blade release during installation.
Since we've moved toward the front of the car, let me introduce a new feature in the engine compartment. It's a brand new idea in oil filters. The filter has a replaceable element as before, but the container is entirely new. It consists of a metal can and a screw-on cap.
The cap is supposed to be tightened by hand only. If you use a wrench, you're liable to ruin the cap or the can. Tell him about it, Gene.
Right, Tech. There's an O-ring type seal in the cap of the container. When the cap is turned down, the seal compresses against the side of the can. If the cap is screwed on too far, the seal will be ruined by the threads on the can. Just in case you have big muscles, there's a stop built into the cap and can. When the cap is screwed on the right distance, a hole at the end of the cap threads stops against a bump in the side of the can. If you used a wrench to tighten the cap, you could force it past the stop, ruining the seal and possibly also ruining the cap and can.
Maybe you ought to explain why there's a hex head on the can.
All right, Tech. Sometimes after a car has been driven 2,000 or 3,000 miles, the combination of dirt and heat will make the cap hard to remove. That's the only time a wrench should ever touch that cap.
Anything new on steering, Pete?
Well, here's a recent change at the steering gear coupling, Tech. It's a new method of anchoring the coupling to the steering gear worm shaft. The lock bolt retainer has been replaced by a steel roll pin. The new coupling is interchangeable with the one that uses the lock bolt. Now, if it's necessary to disconnect the steering shaft coupling from the worm shaft, always use a new roll pin when they're being reassembled.
Here's another tip, Pete. On the first type coupling with a lock bolt, be careful when you're tightening the bolt. The correct torque is 200 inch-pounds. If you go over that amount, you might twist the head off the bolt. Now, if someone will please turn the record, we'll get on with some more 65 service tips. Pete, you have quite a reputation for being able to track down wind noises. How about passing along some tips to all the other technicians?
I'll be glad to, Tech. You can't always tell just where a noise originates. You might start tracing a whistle in one area and wind up finding it in a spot that seems to be totally unrelated. Another thing that makes wind noise diagnosis tough is the fact that the noise will probably change according to operating conditions. Now, for instance, wind speed and direction can have a strong influence on the noise. And as little as 5 miles an hour difference in car speed might bring in the noise or eliminate it. Noise locations may also vary from one car to another, even when the two cars are identical in model and body style. So there's no doubt about it, wind noises can give a technician a real bad time. We've adopted a few procedures that take some of the uncertainties and frustrations out of wind noise tracing. The basic operation, and still the most important step, is a thorough road test. However, before road testing, check the alignment of all the doors and windows. In many cases, adjustment of a door or window will eliminate the source of the noise. This is especially true on hardtops.
On hardtops, be sure the windows seal properly against the roof rail weather strip. Also, check the seal between the front and rear windows. You'll find procedures for making any necessary adjustments in previous reference books and your service manuals.
Right, Tech. And don't forget that the roof rail weather strip retainer is also adjustable in and out. The attaching screw holes are slotted to allow for some movement. If there are any loose moldings, tighten them. Cover any protrusions or openings in the moldings with tape during the test. Seal around the outside of the windshield reveal moldings before road testing. Press rope-type sealer into the opening and smooth it off with a trim stick.
Another spot that might need some of that rope-type sealer is the drip rail. Take a close look at the seams and see that they're sealed up.
Thanks, Tech. Most of the wind noise complaints center around the vent wing area, and they can be pretty tough to pinpoint. Now, here's how we do it. Seal the vent wing and cover the opening between the front of the door and the windshield pillar with masking tape. Then drive the car to see if the noise has been eliminated.
I notice you overlap short sections of tape to seal the openings, Pete.
Right, Tech. That's so we can remove it a little bit at a time while the car is moving. If there's no noise with the tape applied, you can be pretty sure you've located the general area of the air leak. To pin down the exact location, maintain the car speed at which the noise originally occurred. Open the window, peel the tape from the door opening and windshield pillar one section at a time, and close the window. If the noise comes in, mark the spot and reseal the opening. Then, pull the tape from the vent wing to see if there's an air leak there, too. If there is, you'll probably hear a high-pitched whistle. A noise that comes in when the tape is removed from the front of the door opening is probably the result of poor weather strip contact. The weather strip may be distorted or torn loose. Check the weather strip contact by closing the door on a shipping tag. Pull the tag out of the door and note whether the weather strip is gripping the tag. Distorted or torn weather strip should be replaced if it doesn't provide good sealing contact. Sometimes you can improve weather strip contact by inserting a closed-cell foamed plastic shim under the weather strip. Another method is moving the weather strip outward slightly.
Be sure to read the reference book for this session. You'll find some dope on noises that can be mighty tough to trace. There's one in the fresh air plenum chamber, and even the door hinges get into the act. Any other good tips on body service?
We had to replace some tailgate windows on some of our station wagons before we found out what was chipping the glass. As you know, that's a tempered glass, so if it gets chipped or scratched, it will eventually break altogether. We found that the glass was hitting one of the weather strip retaining screws when the window went closed. The screw wasn't installed straight, so the weather strip didn't provide enough clearance. We haven't had the problem lately, but we still inspect all the weather strip retaining screws.
There's been a change in that weather strip, and the new retaining screws have thinner heads, so the clearance has been increased.
Thanks, Tech. I have a couple of items on air conditioning I'd like to talk about if we have time.
For you, Gene, we'll take time. Carry on.
On some of the cars with a reheat-type air conditioner, condensation caused a severe window fogging problem when the defroster was turned on. Early in the spring, when the days were hot and the nights were cool, people used air conditioning during the day and heaters when it cooled off at night. The condensation from the air conditioner was blown out through the heater and defroster outlets. That misted up the windows real quickly. Another condensation problem comes from operating the air conditioner with the independent side vents open, especially in humid weather. This one is easy to spot, though, because the customer will usually complain that he isn't getting enough performance from the air conditioner. Of course, the most obvious reason for condensation discharge is an accumulation of water in the drain pan, so make sure the drain tubes are not plugged with dirt or sealer. To avoid the window fogging, we advised our customers to run the air conditioner for about a minute before turning the heater or defroster on. That blows the moisture out of the system.
Let me interrupt here, Gene. I've heard some reports of independent air conditioning specialists substituting refrigerant 22 for refrigerant 12 when they recharge a system. Don't ever do it. Don't even use a partial charge of refrigerant 22 in our systems. You'll wind up with head pressures as high as a kite, and the mixture of the two refrigerants will ruin the seals and corrode the lines. Our air conditioners are designed to use only refrigerant 12. If you use anything but refrigerant 12, you're just asking for trouble.
Okay, Tech. We'll sure stick to refrigerant 12.
What's on the schedule for the next session, Tech? It's about time for the new models, isn't it?
Right you are, Pete. And the way things look right now, we'll have a lot of new features to talk about. But like you said, that's next month's story. Be sure to be on hand. Greetings, men. What's the big discussion about?
Hi, Tech. Hank was just about to explain some of the body electrical circuits to me.
That's right, Tech. I'd like to kind of review some of the circuits that haven't changed and talk about some of the new circuits for 1965.
Good idea, Hank. Lead on.
Let's take turn signals first. Although the circuit looks complicated, it's really simple if you take it in sections. First of all, notice that there are two supply leads to the turn signal switch, one from the flasher unit and one from the stoplight switch. The stoplight switch is fed from the fuse block. The flasher unit is connected to the ignition switch accessory terminal. With the turn signal switch in neutral, the stoplight circuit goes through the turn switch and to both rear lights. Now let's see what happens when we signal for a left turn. The movable contacts connect the flasher unit lead to the left stoplight filament, the left front turn signal filament, and the left indicator lamp. The stoplight circuit then feeds only the lamp on the right side of the car. For instance, in our example, the left turn signal is flashing, so the right lamp is available for a stop signal.
I noticed that the turn signal bulbs on each side are wired in parallel. How do you tell if one is burned out?
By the flasher operation, Bob. You see, the flasher is set to open the circuit under a specific load, like a circuit breaker. If part of that load is removed, then the flasher operation stops. There's one exception to this. If an indicator lamp burns out, you'll still have flashing turn signals. It's easy to spot this condition because you'll still be able to hear the flasher clicking.
Here's another diagnosis tip, Bob. Losing the ground at one of the front turn signal lamps will stop the flasher action. Instead, both parking lamp filaments will glow dimly. Here's the reason. The parking lamp feed connects the two filaments, so the turn signal current follows right through to the ground on the other side.
Well, that should be easy to check out. I'll just turn on the parking lights, and if one of them doesn't light, but it comes on dim when the turn signal is turned on for that side, then I'll know it's a bad ground.
Nice going, Bob. I think Hank has a couple more tips for you.
I sure do, Tech. If you suspect a flasher unit, try it in both turn positions. If it works in one direction but not in the other, the flasher's okay. The trouble is either a bad bulb, a bad ground, or a loose connection. When the turn signals don't work on either side, see if the heater and radio are operative. They also get their power from the accessory lead of the ignition switch. If they're okay, install a new flasher unit.
I know that some of the cars have only one indicator light. How is the single bulb wired into both left and right turn circuits?
Well, Bob, the basic turn signal circuit is the same as the systems with two indicators. The case of the single indicator bulb is not grounded, but is connected to one of the front turn signal leads. The ground is obtained through the turn signal filament on the opposite side from the intended turn.
So on a left turn, it grounds through the right-hand bulb. But why doesn't that bulb light too?
That's a fair question, Bob. The indicator bulb causes a high voltage drop. That doesn't leave enough voltage to heat up the right turn signal bulb.
And that's a fair answer, Tech. Now here's another question. I understand we have some brand new power window circuits.
That we do, Bob. In fact, the whole system is new on Furies, Poleras, Custom 880s, Monacos, and the entire Chrysler line. Right, Hank?
Right, Tech. For one thing, the window lift motor is a permanent magnet type. All the motors are grounded at a common point, which greatly simplifies diagnosis of possible wiring difficulties. All circuits are grounded through a single terminal in the master switch at the left front door. Each door switch has an individual hot lead. The overall circuit is protected by a circuit breaker located inside the left cowl panel. To understand how the system works, let's look first at the operation of the left front window and the master switch. Then we'll tie in the circuits to the other windows. Notice that when the switch is in the neutral position, both of the movable contacts are closed to ground. These movable contacts become motor feed and motor ground when the switch is operated. Moving the switch in the down direction pushes one of the movable contacts against the battery contact in the base of the switch, completing the down circuit to the motor.
Since this is a permanent magnet motor, I guess you just reverse the direction of current flow to run the window back up.
I'd guess Bob's been studying some basic electricity, wouldn't you, Hank?
I sure would, Tech. And reversing the current flow is as simple as pushing the switch in the other direction. This allows the movable down contact to return to ground and pushes the up contact against the hot lead. Control of the other 3 window lift motors from the driver's seat is just as simple. Current flow through the applicable master switch is exactly the same as for the left front window lift. The individual lift switch must be in the neutral position to allow control from the master switch. Current flows both to and from the motor through the upper contacts of the switch. The direction of the flow, which determines the rotational direction of the motor, depends on the position of the master switch. Control of the window from the individual lift switch involves a slightly different circuit. Both terminals in the base of the switch are hot and feed one of the movable terminals when the switch is operated.
Let's see now. You said the only ground in the system is at the master switch. So the current must flow through the motor, back through the individual switch, and to ground through the movable contact in the master switch.
Exactly right, Robert. Of course, the direction of the current flow through the motor determines which ground terminal is used.
The switches are held in the panel by spring clips. Checking the window lift circuits is a pretty simple matter. Most of the tests can be made without removing the trim panel. If none of the windows will operate from either the master switch or the individual switches, check the single ground connection at the master switch and the battery lead to the circuit breaker. To check the ground, pull the switch and connector from the door trim panel. Connect a jumper wire between a good ground and one of the leads to an individual switch and try that switch in both directions. If the window operates, you'll know the trouble is in the master switch. That's because the only ground in the circuit is at the master switch, not at the motor as on previous systems. Now, here's another tip. If a window operates from the master switch, but not from the individual switch, use a test light to check continuity between the circuit breaker and the individual switch.
I think I can anticipate the next one, Hank. It probably won't happen very often, but a window that operates from the individual switch and not from the master just has to be caused by a bad master switch if all the other windows work normally. Here's the way I figure it. The single hot lead to the master switch feeds the master switch circuits to all 4 windows. It's not likely that one would be dead unless all 4 of them were. The one common connection between the master switch and all the other switches is the ground. So if the ground is bad, the window lifts won't work from any switch. The only answer is that the hot circuit inside the master switch has gone haywire, and that means a new master switch. Does that make sense, Hank?
It makes a lot of sense, Bob, but not all the problems are electrical. Sometimes a mechanical hang-up causes inactive windows. Bent or binding linkage and pinched channels are the most common mechanical causes of window problems. It's easy to identify mechanical problems since there will always be at least a slight movement of the glass.
If you have to take the motor off the linkage, be sure to clamp the assembly in a vise so the linkage is locked in place. If you don't, the assist spring will flip the linkage, and it could cost you some skin. And if someone doesn't flip the record, it could cost us a new needle.
Before we move away from the doors, let's look at the electric door locks. The Imperial system is the same as last year. However, a new system is used on other models. Let's cover it first. Essentially, the new system contains a double-acting solenoid in each door and 2 switches in each front door. Back door locks are operated mechanically with the back door push buttons, but they can also be locked and unlocked remotely from either front door. Pushing down on either of the front door lock buttons momentarily closes a circuit between the circuit breaker, located inside the left cowl panel, and the door locking relay inside the right cowl panel. The energized locking relay completes the circuits to the locking windings in all 4 of the solenoids. Each solenoid is grounded independently to the door inner panel. To unlock all 4 doors, simply pull up on either front door button. This energizes the unlocking relay, which completes the circuits to all 4 solenoid unlocking windings.
Well, since there are switches only at the front doors, it looks like the back doors can be locked or unlocked separately.
Yep. The rear door solenoids just hook onto the regular linkage. That's why the rear lock buttons move when you lock or unlock them electrically from the front.
Right, Tech. There's another lock switch actuated by the key cylinder linkage. When either front door is locked with the key, all doors lock automatically. The circuit is the same as when the lock button is pushed down. When either front door is unlocked from the outside, the lock cylinder linkage moves the switch arm upward without closing any electrical circuits. That's why all the rest of the doors remain locked.
Well, how about service procedures? There doesn't seem to be much that can go wrong.
You're right, Bob. There's only one simple adjustment at each door to provide the correct amount of solenoid travel. If you can hear the solenoid working, but the door doesn't lock, remove the trim panel and loosen the solenoid mounting screws. The mounting holes are elongated to allow correct positioning. The Imperial locks are the same as last year's. Here's the main difference between the Imperial and the new system. The Imperial front push buttons will lock all 4 doors, but pulling the button up unlocks only that one door. A separate switch on each front armrest locks and unlocks all 4 doors.
You'll find more on electric door locks in the reference book for this session. Now, Hank, you'd better cover the windshield wipers on the 65 models.
Coming right up, Tech. We have a new single-speed wiper motor that's standard on Furies, Polaras, Custom 880s, Monacos, and some Chryslers. It's a permanent magnet-type motor. The circuit is very simple and easy to understand. The wiper switch has a built-in circuit breaker between the battery terminal and the combination terminal marked P1 and backup. This is also the feed terminal for backup lights, so it's always hot when the ignition is on. Turning the switch on connects the A terminal to the battery feed through the circuit breaker and P1 terminal. The current flow is through the armature to ground. When the switch is turned off again, the current goes from the P1 terminal to the park switch in the motor, back to the P2 terminal at the switch, and then to the armature from the A terminal. As the blades reach the park position at the end of the wiping pattern, the park switch opens the circuit from the P1 terminal and switches to ground.
But the armature already has one ground. Why do we need a second ground?
So the blades will always park in the correct position. You see, the motor has a tendency to coast after the current is shut off. Since the armature windings are cutting through the magnetic field of the permanent magnet, the coasting motor then becomes a generator. Both output leads are grounded, so the generator is subjected to maximum load, which means maximum drag on the armature. You might run into a little bit of confusion on the single-speed wiper switch, Bob. We're still using a wound field type single-speed motor on some models, but we use the same switch. However, we don't use the P2 switch terminal with the wound field motor.
Well, that's plain enough, Hank. How about service procedures?
Well, the motor is mounted in the engine compartment in these cars, which means it is real easy to get to. The park switch timing adjustment is the only service required on the motor. To adjust the park timing on either single-speed motor, loosen the 5 retaining screws on the gearbox and turn the metal cover plate. Turn the plate to the left if timing is late, or to the right if timing is early. On variable speed motors, the adjustments are made in the opposite directions.
We have 2 different suppliers of these variable speed motors, Bob. There's a little difference in the adjusting procedure. One motor has a nylon plate with a hex in the middle to take a wrench. On the other, you loosen the 5 screws and turn the metal cover plate.
Right, Tech. And here's an easy way to tell if the parking timing is off. If the blade parks and then goes up slightly, the timing is late. If the blade moves down before moving up when the wipers are first turned on, the timing is too early.
That's a good one to remember. It looks like the wiper linkage is easy to get at in these cars.
It is, Bob. Just remove the lower windshield molding and the vent grill panel, and the whole works is right there. Here's another tip. When you get all the retaining screws out of the grill panel, close the hood before you try to lift the panel out.
You'll have to remove the pivot bezels, too. And we have a new special tool for removing the wiper arms. And most important of all, disconnect the battery, or at least remove the ignition key, before you work on the wiper linkage. If you don't, and you happen to move the crank arm enough to close the park switch, the motor will run through the park cycle and maybe take your fingers with it.
I'll be sure to remember that one, Tech. What about wiper blade adjustments?
Well, the variable speed wipers park against the windshield molding. To check the parking, lift the tip of the arm toward the top of the windshield with a force of about 3 pounds. The tip of the blade should not move more than 3 inches from the molding. Both types of single-speed wipers park at the lowest point of the wiping pattern. The tip of the blade should not touch the molding when you push down on the end of the arm with about 3 pounds force.
Those wiper arms look exactly alike. Are they interchangeable?
No, they're not, Bob. If you look real close, you'll see a slightly larger angle on the left arm. And if you look even closer, you'll find that they're stamped L and R on the underside near the blade end.
Here's one that's been bothering me, Hank. I know that variable speed wipers park by reversing the motor, but how do they travel beyond the wiping pattern?
There's a spring and cam assembly between the wiper motor arm and the pivot connecting link. Here's what it does. While the wipers are running, the spring release inner tab releases the spring from the pin, allowing the pin to turn freely. When the motor rotation is reversed, the spring release stop tab moves away from the notch in the pivot linkage. The spring tightens on the pin, causing the cam, spring, and spring release to rotate 180 degrees. The cam rotation lengthens the reach of the pivot connecting link by about 1/4 inch.
It's important that the parking switch timing be adjusted to stop the motor when the linkage is longest.
Right, Tech. And lubrication is important, too. If the drive pin wears to the point where the spring won't grip it, the wipers just won't park in the right position. The spring and pin should be greased any time the unit's disassembled. The only approved lubricant is Chrysler Parts lead plate. Open the spring with snap ring pliers so all the coils are separated. Then dip the spring in a can of lead plate and replace it over the pin. This way, you'll be sure that every part of the spring and pin will be lubricated.
How do I check whether the pin is causing parking problems?
Very simple, Bob. Peel back the protective boot and see if you can turn the trip release ring. If it moves at least 1/32 of an inch, the over-travel mechanism is okay. There's one more thing you ought to know about, Bob. We have additional protection in the wiring this year. There's a new fusible safety link between the starter relay and the ammeter.
Excuse me for interrupting, Hank. That story about the fusible link is real important as well as interesting. But we're running out of time. So, all you technicians had better check the reference book for the complete story on this, and more details about the other circuits we've been talking about. This is one of the service departments I always look forward to visiting. Norm and Marty in a huddle back there are usually worth listening to. Let's find out what the conference is all about. Say, Norm, what are you and Marty up to this beautiful fall day?
I guess you might say that we're plotting against the cold weather that's just around the corner, Tech. Actually, we were just comparing notes on winter season service and sort of picking each other's brains on solving or preventing cold weather starting and performance problems.
Sounds timely and interesting, Norm. Now tell me, Marty, is this a private party or is it open to the public?
You didn't have to ask that, Tech. You know you and your master technician friends are always welcome to listen to our opinions and experiences. Matter of fact, I hereby nominate you to moderate this seasonal service gabfest.
I'll just take you up on that and kick this session off by asking you how much importance you attach to battery service.
The battery sure isn't as frequently a cause of cold weather problems as it used to be, thanks to the alternator, 12-volt electrical system, multi-viscosity oils, and a lot of other design improvements. However, the battery's specific gravity test still heads the list of things to check on every tune-up or winter service job. Now, that's because a low battery is bound to cause cold weather starting problems. A fully charged battery is good insurance against won't start complaints. While I'm at it, I make sure the battery is clean and make sure there are no leaks or cracks in the sealing compound that would promote excessive self-discharge. This is particularly important on high mileage and older cars. Clean, tight battery cables are always important. On older cars, I take the cables off, clean the battery posts and the cable terminals.
After you reconnect the cables, coat the battery posts and cable terminals with light grease. That's good insurance against corrosion. And the right capacity battery is good insurance against starting trouble. Underpowered bargain batteries don't have the capacity to deliver a hot spark and good cranking speed in extremely cold weather.
Good point, Tech. Too often I find an underpowered battery in an old car where a little extra capacity is what the owner should have bought. Even for a relatively new car, a heavy-duty battery is a good idea under extremely difficult starting conditions.
It seems to me that should just about take care of the discussion on the importance of the battery. Unless you have something to add, Norm.
I would like to express an opinion on a closely related subject, the battery charging system. Anytime I run into a dead battery, a low battery, or a chronic case of hard starting, I make it a point to check out the entire charging system.
You might say a dead battery calls for a scientific autopsy on the charging system.
That's about the size of it, Tech. I don't mean to suggest that a soup-to-nuts test of the charging system is a seasonal service that should be performed on every car that comes in, but I am convinced that the charging system should be tested any time a customer has battery trouble.
Amen, Norman. And I'd like to add, the battery, the field circuit, the charging circuit, the alternator, and the voltage regulator are all part of the charging system. Test them all, test them in order, follow the manual. No shortcuts, please.
On the other hand, if the battery is okay, but hard starting is the complaint, I recommend running a cranking voltage test to find out if input voltage to the ignition coil is high enough to ensure good coil output when the battery's under a cranking load. Now, here are a few clues I get from cranking voltage and speed. If the battery is okay, but cranking speed seems slow, I check out the entire cranking circuit before I worry about the primary ignition circuit. On the other hand, if cranking speed is good, but the cranking voltage test shows that primary ignition voltage is low, I check out the primary ignition circuit resistance. Now, this may sound kind of elementary, but it's a mighty important step in tracking down hard start or won't start problems.
Inspecting ignition points for evidence of burning or excessive pitting is kind of fundamental too, Marty. But ignition point condition, alignment, and spacing is a service that isn't always done as carefully as it should be.
That's for sure, Tech. For instance, always pull the distributor to install ignition points so you can check out the advanced curves, test the breaker arm spring, align points properly, and gap them accurately. It's next to impossible to install and align points properly without pulling the distributor.
A thin film of special Mopar or Chrysler distributor cam lube will cut down rubbing block wear. Too much lube or the wrong kind of lube will cause burned ignition points. Next, I'd like to get in my 2 cents worth on condensers. The condenser has an extremely long service life, and condenser failure is seldom a cause of ignition point trouble. If the car can be started at all, you can bet the condenser hasn't failed. On the other hand, an off-brand condenser that isn't matched to the ignition coil and the ignition system will affect engine performance and can cause premature point failure.
Norm's right. And that means there isn't any good reason to replace a condenser unless it's failed completely or was the wrong capacity to start with. Here are the common causes of premature point failure: excessive oil or lube, the wrong kind of cam lube, A point gap that's too close? Or high voltage because the voltage regulator's set too high? Now, how about a word to the wise on secondary ignition problems, Marty?
Coming up next, Tech. Present-day ignition systems put out as much as 20,000 volts. Now, if that kind of voltage gets half a chance, it will jump to ground before it gets to a spark plug. That's why the higher ignition voltage requirements of modern high-compression, high-speed engines make it necessary to pay particular attention to the condition and servicing of the secondary ignition system. We usually think of secondary ignition problems, particularly ignition cable and nipple problems, in connection with wet weather starting troubles.
I've got a word or two to say on that score, Marty. You fellas up here in the snow country gotta remember that in some parts of the country the winter season is the wet season. It's also important to remember that north, south, east, or west, marginal secondary or primary ignition performance may provide satisfactory starting in hot, dry weather, but serious starting problems in damp or cold weather.
I'll buy that, Tech. And a combination of damp, cold weather is real trouble for a faulty ignition system. Now, I don't have any hard and fast rule on where you ought to start looking for trouble in the secondary system or what you should do first to prevent trouble. I guess everything is important, and it doesn't make much difference where you start as long as you hit everything. Always assume the coil tower has a film on it that might lead to carbon tracking and clean it. Then, inspect it for cracks or other damage. Also, inspect the cable nipple, the cable, and the cable terminal.
The eraser end of an ordinary lead pencil makes a good tool for cleaning out the inside of the coil tower and, of course, the distributor cap towers. This is particularly important on high mileage and older cars. Clean and inspect every spark plug cable and nipple. Unless every cable is in perfect condition and properly routed, you're asking for starting trouble in cold, damp days. When you connect a timing light, use an approved adapter. Don't ever use a timing light or other test equipment that requires puncturing or that may damage the insulation of the high-tension ignition cables.
Speaking of cables, I'm sold on the superiority of the high-tension ignition cable sets we're now getting from the Chrysler Parts Division. Anytime I replace nipples or cables, I stick to the recommended replacement parts. Here are a couple more tips worth remembering. Don't slide a nipple on the cable. If you do, you'll reduce the effectiveness of the nipple-to-cable seal. Whenever you install a cable and nipple, pinch the cable and nipple to release trapped air and push the cable terminal all the way into the coil or distributor tower. I've seen cases where this wasn't done, and the nipple and cable popped up, leaving a poor contact and a poor seal. I'm sure that by now, everyone should know how important it is to make sure the distributor cap is clean, inside and out. Yet, I still run into starting and wet weather performance problems that are caused by a cap that hasn't been properly cleaned.
There's only one way to clean a cap right. Get the cap off the car where you can scrub inside and out in a warm solution of a non-inflammable household detergent. When the cap is clean, rinse it with clean hot water. Give it a shake or two and let it air dry. It'll dry in a jiffy if the rinse water's hot. Don't use compressed air. It may contain oil. Of course, after you clean the cap, be sure and inspect it. And that seems to just about cover most of the ignition system. If someone will turn the record over, we can find out what Marty and Norm have to say about getting the fuel system set for the winter season. Norm, it seems to me you've let Marty do most of the talking so far. Suppose you kick off the second half with a few well-chosen words on the fuel system.
Okay, Tech. I think the best way to cover carburation service highlights is to tell you about some of the most common mistakes I've seen made and a few mistakes I've made myself. To begin with, I've seen far too many cases where the carburetor came in for a complete overhaul when a minor adjustment would have taken care of the starting or performance problem.
I'm sure the choke doesn't get out of adjustment or cause trouble half as often as some people think it does.
Exactly, Tech. It's seldom necessary or desirable to adjust the choke unless someone else has already misadjusted it. Instead of pulling the choke out of its well at the slightest provocation, Make sure the choke can be fully closed manually. Simply open the throttle to release the fast idle cam and the choke linkage, and use light pressure to close the choke valve. If it doesn't close easily and fully, then it's time to look for the cause of the choke trouble.
I hate to bring up a point we've covered so many times before, but it's still important. On past models with a vacuum piston, make sure the piston is free. Also, make sure the choke valve shaft and bushings are free of gum and deposits. A sticking choke valve shaft is just as apt to cause trouble as a sticking piston. And this brings up another important point. Don't forget to flush the choke shaft and bushings periodically with carburetor cleaner on 64 and 65 models with a vacuum diaphragm setup. I didn't mean to steal a ball from you, Norm. Suppose you take it from here.
Okay, Tech. A bind in the choke linkage or binding of the choke itself in its well are also common reasons why the choke valve won't close fully. To find the trouble, disconnect one link at a time until you find the cause. Whatever you do, don't start bending rods indiscriminately or straightening rods to eliminate a bind until you've checked the service manual or looked at another carburetor of the same model. I've seen a number of cases where bent rods or linkage interfered with choke and fast idle operation. I wonder if all technicians realize the importance of the vacuum kick adjustments, Tech.
I don't know, Norm, but I'll bet everyone out there will be interested in hearing your ideas on the subject.
Based on my experience, I'd say that vacuum kick misadjustment is more apt to cause choke trouble than the choke itself. For example, if the vacuum kick is adjusted so that the vacuum diaphragm pulls the choke open too far, the choke may not fully close. Of course, that'll cause starting trouble in cold weather. A vacuum kick that's too wide may not be much of a problem in warm or hot weather. However, when it gets cold, the car may not start or will be hard to start. And then during warm-up, the mixture will be too lean, causing frequent stalling.
Two wrongs don't make a right. Don't try and correct this condition by adjusting the choke. Correct the vacuum kick adjustment.
Of course, if the vacuum kick is misadjusted so the kick opening is too narrow, well, the starting and warm-up mixture will be too rich. This would cause the engine to roll erratically and stall frequently from over-choking. Here are some suggestions on adjusting the vacuum kick. You must apply at least 10 inches of vacuum to the vacuum diaphragm when adjusting or measuring the vacuum kick. If you don't have a vacuum pump handy, use the manifold vacuum from the car in the next bay. All you need is a long length of vacuum hose.
Any engine that'll run will probably pull more than 10 inches of vacuum. Any more good vacuum kick suggestions, Norm?
Sure, Tech, I'm loaded with free advice. For example, be sure and use 64 model vacuum kick specs for 64 models and 65 specs for 65s.
There's a lot of difference between the two. I don't try to remember them. I use the service manual. Not long ago, I had a job that was over-choking. I checked and rechecked everything, including the vacuum kick adjustment. I finally found out that the vacuum diaphragm was leaking. Since that experience, I leak test every vacuum diaphragm before I test or readjust the vacuum kick.
Why don't you explain that test, Marty?
All you do is push the vacuum diaphragm stem to the fully retracted position. Then, put your finger over the tiny hole in the end of the vacuum hose connector of the vacuum diaphragm. As long as you hold your finger over the hole, the diaphragm stem shouldn't budge. If it does, the unit's leaking and should be replaced.
I'd like to pass on a tip or two on the vacuum diaphragm kick mechanism used on this Stromberg carburetor. Don't ever bend this wire spring, or you'll upset the calibration of the vacuum kick mechanism. That tab with a square hole in it is there to protect the spring from getting bent accidentally. Another thing, make sure the choke diaphragm link is installed on the correct side of the wire spring. If the rod is installed between the spring and the end of the slot, the spring will get bent and choke operation will be all wrong.
Good advice, Tech. I make it a rule to eyeball the wire spring to see if it is straight and properly positioned before I work on a 65 Stromberg.
By eyeballing, Norm simply means to use your eye to see if the spring's straight. Have you noticed the big improvement in engine performance during warm-up on the 65 models?
Yeah. The fast idle speed gradually decreases as the engine warms up, whereas on past models, fast idle seems to gradually increase during warm-up and then suddenly drop back to curb idle.
Correct fast idle speed adjustment is very important because it establishes the correct position of the fast idle cam with respect to the choke. Don't overlook the importance of precise fast idle adjustment, particularly in cold weather. Do adjust curb idle and the idle mixture first before you attempt to adjust fast idle. If the idle mixture is off, fast idle and warm-up performance will not be right.
Here's a good rule for setting idle mixture and idle speed. With engine fully warmed up, adjust to get the best lean mixture setting and the highest specified idle speed. This'll give you the best all-around performance and economy.
You can also minimize stalling due to icing by setting idle speed at the high limit, mixture on the lean side, and fast idle right on the specified button. Here's why. Ice forming between the edge of the throttle blade and the carburetor body chokes off the air and causes stalls. Now, if idle speed is adjusted to the high limit, the opening between the blade and the carburetor body will be wider. As a result, it'll take a lot more ice to choke off the airflow completely. Furthermore, because icing reduces airflow, it increases the richness of the mixture. If the idle mixture is on the lean rather than the rich side to begin with, it'll tolerate a lot more enrichment due to icing without stalling. While we're on the subject of icing, carburetor icing and stalling during warm-up is apt to be a real serious problem if the manifold heat control valve isn't free.
A shot of Mopar or Crico manifold heat control valve solvent on the valve shaft is good cold weather performance insurance.
The carburetors on all engines equipped with closed crankcase ventilation are calibrated to match the controlled vacuum bleed provided by the crankcase vent valve. If the crankcase vent valve is plugged, the idle mixture will be too rich, causing rough engine idle. This will also aggravate stalling due to carburetor icing. If the vent valve gets stuck open, the idle mixture will be too lean for smooth idle and good low-speed engine performance.
In other words, make sure the vent valve is free. If it isn't, it should be replaced.
That's a good point, Tech, and here's another. Float level adjustment and complete carburetor overhaul certainly can't be considered as seasonal services. Unless high mileage on the car or a specific complaint calls for checking float level, don't take the carburetor off or disassemble it. Do test the accelerator pump discharge by opening the throttle quickly by hand. A solid, continuous stream indicates that the plunger and the valve are probably okay. On 2 or 4 barrel carburetors, the 2 discharge streams should be about the same. It's also a good idea to check the accelerator pump stroke and adjust it to specifications if it isn't right. Correct pump stroke is important in connection with acceleration performance in any weather. Well, that takes care of winter service highlights on the carburetor. Now, I'd like to put in a word or two on seasonal cooling system and lubrication service. Now, these items should be
Whoa there, Norman. We've just about run out of time on this record, so I guess they'll have to open their reference books and find out what you were about to say on cooling and lubrication service. As a matter of fact, I wish all you out there would think about the service tips Marty and Norm have covered today, and take time to read your reference books. I'm sure that even the best of you will pick up a tip or two that'll help you do a better job. Don't ever forget, a lot of people are depending on you master technicians to keep them rolling, keep them happy, and keep them buying Chrysler-built cars and trucks. Makes you feel important, doesn't it?
Say, Pete,
That's a rig I haven't seen before, and yet it looks vaguely familiar.
Well, you've seen part of it before, Frank. It's the prop shaft angularity gauge, with an adapter for measuring the front U-joint angle. Now, this engine adapter, fastened to the prop shaft gauge, is a lot easier to use and more accurate than the old method using a protractor. And believe me, these drivetrain angles have really become important in the last few years.
I know they're important, Pete, but, well, I'm not sure I know just why they're important.
Well, let's go talk it over with Tech. There might be 1 or 2 points I'm not clear on.
Greetings, men. Pete, I'd say if that gauge you're carrying is any indication, we're gonna talk about universal joint angles. How's my guesswork?
It seems like you never miss, Tech. To start off, I think we should establish the importance of universal joint working angles and their effect on noises and vibrations.
Sounds like a good start. Lead on, Pete.
If we could have a perfectly straight connection between the transmission and differential, we could eliminate a major source of vibration and noise problems. Now, unfortunately, this isn't possible. And here's why. First, the differential is constantly moving up and down in relation to the transmission because of bumps and low spots in the road. In addition, acceleration and deceleration cause the rear axle housing to rotate slightly, raising or lowering the nose of the differential.
Well, that brings me back to my question, Pete. If the U-joint angle is subject to all these changes, why is the tolerance so close when we set the angle?
That's a good question, Frank. Wonder if Pete has a good answer.
Well, I sure do, Tech. The large variations in the differential angle are caused by temporary conditions. And when the condition changes, the differential returns to a normal position. Here's an example. During quick acceleration, the reaction from the rear wheels throws a heavy torque load on the axle housing. The torque deflects the springs, so the differential nose comes up quite a bit.
It could come up as much as 15 degrees.
Right, Tech. And since our normal U-joint angle when the car is standing still is 1 to 3 degrees below the center line, a 15-degree rise during acceleration would put the U-joint angle well above the center line. Then, as car speed increases and the torque load decreases, the differential nose comes down until, at a normal cruising or road load torque, the U-joint operating angle is very near 0 degrees.
That's clear enough. But U-joints are supposed to drive through angles, so what's wrong with having a big angle?
But when a universal joint operates at an angle, the driving member and the driven member are rotating through different planes. Now, let's use the front U-joint for an example. The driving member attached to the transmission output shaft runs at a constant speed throughout each single revolution. So, each 90 degrees of rotation takes the same amount of time. The driven yoke, of course, has to turn at the same RPM as the driving yoke. But because it's turning through a different plane, it has to speed up and slow down twice during each single revolution. So, every 90 degrees, the driven yoke and prop shaft change their speed of rotation. Now, this rapid acceleration and deceleration sets up alternating forces of inertia in the prop shaft.
If that sounds a little confusing to you, Frank, just keep in mind that the prop shaft is pretty heavy. And when that weight is accelerated and decelerated rapidly, it produces a vibration.
Right, Tech. And as the rate of acceleration and deceleration is increased, the amount of vibration is also increased. Now, that's where the size of the operating angle comes in. We know that if the universal joint were perfectly straight, both yokes would turn in the same plane. There would be no acceleration and deceleration problem to cause prop shaft vibration. As the operating angle increases away from the perfectly straight position, the rate of acceleration and deceleration is greatly multiplied. So we have more and more vibration.
Well, I can see now why we need to be extra careful in checking U-joint angles. How about a refresher in checking out a prop shaft vibration complaint?
I wouldn't be surprised if that's exactly what Pete has in mind.
Right again, Tech. I have a 3-step procedure that I follow on these problems. First, I road test the car. Then I make a thorough inspection. and then I measure the U-joint angle. I always try to get the customer to go with me on the road test. He can help to pinpoint the specific problem. Now, it might be something completely unrelated to his original complaint. Find the smoothest road available and try the car throughout all speed ranges to determine whether the noise or vibration comes in at low, medium, or high speed. Now, this can help you to eliminate some possible causes.
There's a whole section on prop shaft disturbances in relation to car speeds in the reference book for this session. It can save you a lot of hunting time.
Thanks, Tech. I'll remember that. When you're road testing a car, how do you separate the prop shaft noises from others such as tire noises?
We'll be talking about tires in a few minutes. But what about other noises, Pete?
Well, I always judge by the speed range that brings in the vibration, and whether I can actually hear the noise or if I can only feel a vibration. For example, if I feel a shudder during normal acceleration at very low speed on cars with automatic transmission, I can usually count on finding too much front universal joint angle. Now, to correct the angle, use a shim between the transmission extension and the rear engine mount. Low-speed roughness at speeds of about 25 to 40 are usually caused by too much operating angle at the rear U-joints. Now, during light acceleration, you can hear the noise as well as feel the vibration. The noise may also be present during coast and road load conditions, but will probably disappear under wide-open throttle acceleration. A pretty sure way of curing low-speed roughness is to use a tapered shim between both rear springs and spring seats. Place the thick end of the shims forward to reduce the U-joint operating angle.
Low-speed roughness might be caused by a worn front universal, too. If you repair the universal joint, check all the parts for wear, and be extra careful to get everything centered properly, so you don't cause an unbalanced condition.
Now, if you get a high-speed vibration at about 60 miles an hour and higher, a couple of additional tests are in order. First, of course, make sure that you have a clear highway. Then, bring the speed up until the vibration comes in and pop the throttle wide open for 2 or 3 seconds. The vibration will probably increase. Next, shift the transmission into neutral and see if the vibration disappears. If all these symptoms are present, you'll probably have to decrease both front and rear U-joint angles. After the road test, make a thorough inspection. Check for sagging or broken springs, worn spring bushings, and loose spring U-bolts. Check the prop shaft, too. A small amount of undercoating material or a dent in the shaft could throw it out of balance. A dent could also mean that the shaft has been bent out of line, so check the prop shaft runout. Check runout at both ends using a dial indicator clamped to the transmission and differential. Maximum allowable runout is 25 thousandths. Now, to measure runout at the center of the shaft, clamp the indicator to something solid, such as a seat belt bolt or parking brake cable guide.
We'll have more on prop shaft runout in the reference book. Oh, speaking of runout, we're just about to run out of record. Somebody ought to turn it over.
Quite a while ago, we started talking about this gauge. How about explaining the adapter to me?
We'd better cover the whole procedure, Pete. It's been changed quite a bit to get more accurate readings.
Good idea, Tech. Now, first of all, there must be no extra weight in the car. Check the back seat and the luggage compartment for heavy packages and toolboxes. The fuel tank should be full. If you have to use a twin-post hoist to raise the car, be sure the pads on the rear post are adjusted so they won't twist the axle housing when they contact it. Of course, a drive-on hoist, alignment rack, or pit is best.
Most important of all, don't try to use a frame contact hoist. Why don't you show Frank how to check the prop shaft angles on this car? The new procedure is the same for all models, so if he knows how to check one, he won't have any trouble checking the others.
Okay, Tech. In this new procedure, Frank, start at the engine and then go to the prop shaft. At the rear, you still go from the differential to the prop shaft. Attach the engine adapter to the gauge and place the adapter pins against the oil pan flange. Now be sure the flange is clean. and hold the gauge vertical. Then, on all belvederes and coronets, except station wagons, set the bubble 2 full graduations to the rear of center. Now, this setting will be different on other cars, depending on wheelbase and spring height.
There's a chart in the reference book for this session that gives the correct setting for all the 65 cars.
Thanks, Tech. Remove the engine adapter from the gauge and hold the gauge against the bottom of the prop shaft. If the bubble is centered in the spirit level, the front U-joint angle is perfect. If the bubble is within 1.5 graduations from the center, the angle is still within tolerance.
Even if the bubble is slightly forward of the tolerance area, it's okay. But if it's to the rear, the U-joint angle is too big. If you add a 1/8 inch shim under the rear engine mount, you'll reduce the angle about 1 graduation. After you install a shim, recheck the angle, starting at the engine oil pan.
The gauge reference points on the differential are under the pinion bumper bracket, so you'll have to remove the bracket to make the initial setting. Set the gauge on the 2 machined reference pads and position the bubble according to specifications. In this case, put the bubble 1 graduation forward of the center area. To determine whether the angle is correct, hold the gauge against the bottom of the prop shaft. If the bubble is centered in the level, the U-joint angle is perfect. You have a tolerance of plus or minus 1 degree at the rear U-joint. That means the bubble can be anywhere inside the outer marks and still be within limits. If it's outside, you'll have to insert tapered shims at the rear spring seats.
Here's a good way to remember which way the taper goes. If the bubble is at the front of the gauge, put the thick end of the shim toward the front of the car.
Thanks, Tech. I'll remember that one. I know you make the correction by putting tapered shims between the springs and spring seats. But how much correction do you get from each shim?
That depends on which one you use, Frank.
There are 4 different sizes, with angles of a 1/2 degree, 1 degree, 2 degrees, and 3 degrees. You can use combinations to get within a 1/2 degree of the perfect setting.
Don't ever use anything other than a steel shim. And be sure it's the same width as the springs. There's another important caution here, too. Don't ever use a shim pack that's over a 1/4 inch thick at the center. If you need that much, there's something else wrong, such as a mislocated spring seat. Finally, here's one I shouldn't have to tell you about. When you're tightening the spring U-bolts, use a torque wrench and the shop manual specs.
That's a good pair of tools, Tech. And when you've tightened the U-bolts, it's a good idea to go back and check the universal joint angles again, to be sure that you've corrected the problem.
Some of our 1965 Chryslers have the new constant velocity universal joints at the front. You don't have to worry about the constant velocity joint angles, but be sure to check the rear joint.
Well, Frank, that about wraps up the story on prop shafts and U-joint angles. Any questions?
Just one. Tech, you said a while ago that we'd talk about tires later on. How about it?
I won't try to get off the hook, Frank. With all the new high-speed highways and quieter cars, noises and vibrations from wheels or tires have become more evident. What can you tell them about it, Pete?
Well, the first step, of course, is to find out whether the wheels and tires are actually causing the vibrations. Here are some things to look for in a road test. Tire thump usually comes in at about 20 miles an hour and increases in frequency up to about 45. There isn't much you can do about a thumper except replace it. To determine which tire is the thumper, inflate all the tires to 50 pounds and drive over the same road. This will eliminate or reduce the noise. Then deflate 1 tire at a time to normal pressure. When the thump comes back, the last tire deflated is the guilty one. Tire roughness, which occurs at about 40 to 70 miles an hour, could be caused by 1 tire or by 2 or more thumpers. You might have to use tires known to be good to locate the bad tires. Wheel and tire runout or unbalance cause a high-speed vibration. Now, usually, you won't hear any noise from it, but you'll be able to feel it above 60 miles an hour. First, check the wheel and tire runout. 60 thousandths of an inch or more tread runout on any tire may cause high-speed vibration. That amounts to about a 1/16 of an inch.
Be sure to drive the car 3 or 4 miles before checking runout. That'll get the flat spots out of the tires. Lift the car right away. Then check the wheel bearing preload. A loose bearing could give the same symptoms you get from runout.
Check the sidewall runout, too. 80 thousandths, or about 3/32 of an inch or more here, could also give you problems. If the runout is too high in either place, remove the wheel and remount it 2 studs around on the drum. Then recheck the runout.
Let me get in a word of caution here. When you're tightening those wheel studs, use a torque wrench. Even a perfect wheel and tire can be distorted if the stud nuts are reefed up too tight. Another thing, there's a correct sequence to follow when tightening the nuts. Run them all up just snug, then start around the wheel, skipping every other nut until they're all tightened. It should take about 3 times around to finish the job.
Now, sometimes you can whip a runout problem by relocating the tire on the wheel. Before you remove the tire, make a chalk mark across the tire and wheel at the high runout spot. Now, when the tire is removed, clean the bead thoroughly. Then remount the wheel on the drum and check the bead runout. There should be no more than 45 thousandths lateral runout and 35 thousandths radial runout. If the wheel high runout spot is near the original chalk mark, remount the tire with the tire high spot 180 degrees from the wheel high spot. Anytime a tire has been relocated on the wheel or a new tire is mounted, the tire and wheel should be balanced. And to do the job right, balance it both statically and dynamically. Static balance merely means that the weight is evenly distributed around the center of the spindle. Now, this does not assure dynamic balance, which, in more sensitive cars, becomes important. To explain dynamic balance, let's divide the wheel and tire assembly into 4 equal parts. If all 4 sections have equal weight, the assembly will be in dynamic balance. Now, this wheel, with more weight in sections B and C than in sections A and D, may be in perfect static balance. But when the wheel begins to spin, centrifugal force acting on the heavier sections will tend to push the heavier sections in toward the vertical center line of the wheel. Now, when sections A and B rotate 180 degrees, the direction of the push from centrifugal force is reversed, and the wheel wobbles or shimmies. So, to counteract the centrifugal force, you have to add the difference in weight to the lighter sections.
That clears up the reasons for balancing wheels and tires. But how do you space the...
Whoa! Unless someone adds some space to this record, the needle will be playing on the label. Be sure to study the reference book for this session. There's more good dope on universal joints, wheels, and tires. And remember, the only sounds our customers want to hear will be coming from the radio. Like this. Say, Fred, who belongs to this fine set of hand tools?
A young fellow by the name of Bill Brown, Tech. He just hired in. This is his first day on the job here.
You know, Fred, you always did have a knack for recruiting promising young mechanics. Who did you steal this one from?
Well, if you really want to know, I rescued Bill from an independent shop on the other side of town.
Do you still give every new man you hire your short lecture on the importance of the tools of the trade?
I sure do, Tech. It's mighty important to make sure a new man gets off to a good start. Well, I'm all primed, and here comes Bill now.
Hello there, Bill Brown. I'm Master Tech, and I'm glad to meet you. Fred's been telling me about you.
Fred's told me about you in the Master Tech program, too. I was looking forward to seeing you on the screen, but I hardly expected to find you on the welcoming committee.
I think you're going to like working in this service department, Bill. Judging from these tools of yours, You and Fred should get along fine. Fred knows the value of good tools, and he knows how to use them. How about it, Fred?
Good tools and equipment and trained service technicians who know how to use them are two of the most important ingredients in the kind of customer care that builds repeat service business and repeat car sales. I've looked over your personal hand tools, Bill, and I've seen you use them, so I know that you understand and appreciate good tools. We have more tools and better tools to work with here than most shops. I want you to learn what they are and how to use them. My definition of a tool is anything that helps you do the job better, do the job faster, do the job easier and safely. The tools of the trade include hand tools, special tools, shop equipment, service manuals, service bulletins, and the tech reference books.
No one I know can remember all of the specifications or all of the details involved in servicing all of the cars that come in for service. That's why Fred keeps this complete set of service manuals and bulletins right here with the special tools.
As a matter of fact, Bill, a service manual is one of your most important service tools. It explains all procedures and shows you how to use all of the special tools.
Don't be bashful about using the service manuals. The few minutes it takes to check up on a specification or procedure is time well spent. Chances are it'll save time, and making sure is good insurance against costly mistakes. Now, to get back on the subject of special tools. I've had a lot of service technicians ask me why engineers don't design cars so they can be serviced with standard tools or hand tools.
How do you answer that one, Tech?
Design improvements in our cars can't be limited to the service capabilities of hand tools or standard tools. You might say special tools are the byproduct of progress.
I never thought of it quite that way, but it sure makes a lot of sense. Right now, I think I need a lesson on all these special tools.
It'd probably take all day to explain the use of every special tool we have, but I'll try to cover as many as I can. I have my own way of classifying tools according to the kind of jobs they do. One general class is for servicing bearings, another for servicing precision bushings, and still another for servicing seals. Some tools aren't absolutely necessary, but I wouldn't try to get along without them because they're especially handy. Still others are absolutely unique and indispensable. You just couldn't do the job without them. Work holders, the special stands, jigs, and fixtures save time, save tempers, and protect the assemblies you're working on. Last, but certainly not least, are all the testing and measuring devices. Precision work and accurate diagnosis would be impossible without them.
That's an interesting way of classifying special tools. Are you going to cover some specific examples with Bill?
Although the manuals cover these tools, I want to tell Bill about a few typical special tools and why they are special, essential, and indispensable. This roller bearing puller, or one just like it, has been salvaging good roller bearings for about 35 years. It was introduced about 1930, and it's still an essential tool for 65 models.
What do you mean by salvaging bearings?
By using the correct adapter, costly bearings are easily removed from axle shafts, pinion shafts, and the differential case without damaging the bearings, shaft, or case.
In other words, the bearings can be saved and reinstalled instead of being replaced. Why don't you explain what's so special about the adapter plates, Fred?
The inside diameter and taper of each adapter is designed to match the outside diameter and taper of a specific roller bearing. Each adapter fits easily and quickly into one puller base. The puller pressure exerted on the puller base is transmitted to the adapter. Since the tapered face of the adapter matches the tapered face of the bearing, the adapter presses on the bearing rollers, just like a bearing cup. On a blind-shouldered bearing, the puller can't bear on the bearing hub. Instead, the shoulder of the adapter pushes squarely against the bearing roller retainer. The retainer pushes on the end of the roller, and the roller pushes on the flange of the bearing hub, or cone.
Be sure and use the correct adapter. If the diameter and the taper of the adapter don't match the bearing, the puller will simply pop the rollers out of the bearing. Of course, that'll be the end of the bearing. What's more, once you pull the rollers from a blind-shouldered bearing, there isn't any easy way to get the bearing hub off. If you heat it or cut it off, you'll probably ruin the shaft.
I've ruined more than one bearing using a fits-all puller. We didn't have many special tools in the shop I came from. You should have seen the assorted sizes of pipe we had for installing roller bearings.
Well, it's been years since we used a piece of pipe to drive a roller bearing onto a pinion shaft in this shop. The way I see it, special pinion bearing installing sleeves save bearings, shafts, and time. They are the right length and the right diameter, so there's no chance of pushing on the bearing retainer and ruining the bearing. This differential case side bearing driver has saved enough bearings to pay for itself. It pilots on the bearing taper, making it easy to keep the driver aligned. That way, the driving force is always concentrated on the bearing hub. This eliminates damage to the differential case or bearing. But I think I've spent enough time on roller bearing tools.
Precision-type service bushings are a good example of design progress, Fred. Why don't you tell Bill about some of the special bushing tools?
Good idea, Dick. The new bushings are a lot easier to service than bushings that had to be driven in, bored, or reamed to size and maybe burnished for final finish. Precision bushings must be handled with care. They're finished to very close tolerances, and the running clearances will be upset if the bushing is distorted when it's driven or pressed into place.
You need precision tools and careful handling to service precision bushings right.
You sure do, Dick. For instance, this set of tools services torque flight transmission bushings. I want to give you a couple of examples of why I consider these tools essential. The torque flight input shaft bushing fits into a blind bore in the end of the input shaft. That means you have to pull the old bushing because you can't drive it out. The threaded end of this special bushing remover really grips that input shaft bushing. The hex nut supplies the pulling force, and the special cup puts the pulling pressure on the rear clutch retainer, where it belongs. Installing a new bushing is a precision proposition. If that input shaft bushing is accidentally driven too far into the input shaft bore, the chamfer at the bottom of the bore will distort the bushing. Of course, this would ruin the bushing and cause trouble, if you put the job together that way. This special bushing installing head pilots in the inside diameter of the bushing, and the shoulder of the installing head ensures that the bushing will be driven exactly flush with the end of the input shaft. No more, no less. Some bushings, like the torque flight front clutch retainer bushing, can be driven out because they aren't installed in a blind bore. However, it's important to use the right remover for these bushings too. If you try to punch the old bushing out, you'll probably damage the clutch retainer. Instead, use the special remover head. It'll put all the pressure squarely on the end of the bushing. Support the bushing so it won't collapse and prevent damage to the clutch retainer.
Let me explain the bushing installer. The front clutch retainer bushing must be installed a precise distance into the bore, beyond the flush point. The special installing head has two steps or shoulders. The first one bears on the end of the bushing, and the second one positions the bushing at exactly the right depth. And that, my friends, winds up the bushing story, and this side of the record. So turn it over and hear what Fred has to say about servicing seals.
If there's anything I hate, it's a comeback that's caused by a leaking seal. It seems to me that whenever an owner brings a job back in because of a lube leak, he's questioning the quality of our service work. And, of course, I hate to do the job over just because a seal wasn't properly installed.
Today's seals do a real good job, if you handle them right and install them properly.
You mean I won't have to use a drift punch to install seals anymore?
You better not let Fred catch you using a drift to drive a seal into place. How about it, Fred?
I'll expect you to handle seals with care, Bill. For example, if you install the differential drive pinion oil seal in the housing far enough to bottom against the bearing or the face of the differential housing, you're asking for leak trouble.
Why is that, Fred?
The seal must be positioned so that the sealing lip will seal against the ground sealing surface of the rear U-joint flange. If the seal is driven in too far, the lip of the seal will contact the chamfer on the end of the U-joint flange instead of the ground journal surface. This lets the oil leak past the seal. This special pinion seal driver uses the hub of the pinion bearing as a reference surface to position the seal at the proper depth. Simply install the seal into the housing until the tool bottoms against the pinion bearing.
How about seal removers, Fred?
We have all of the different size buttress thread type seal removers, Bill. They're fast, easy to use, and do a good job on most seals. There's one exception to that I want to ask Tech about. We've had trouble trying to remove the transmission extension housing seal with a buttress-type puller. If the puller screws in too far, you pull the bushing as well as the seal. Is it true that we can get a special puller for that seal now, Dick?
Yes, Fred. The tool is ready for shipment, and a new tool catalog that shows it is on the way. It's a U-shaped tool that straddles the seal. It's tapered so that it actually wedges the seal away from the housing. It works something like an oversized tack puller. It's easy to use and does a slick job of pulling that extension housing seal.
I won't take time now to cover all of our seal removers and installers, Bill. Just remember, though, we have all of the essential and desirable ones, and I'll expect you to use them.
It'll be a pleasure to retire the prick, punch, and drift I've been using to remove and install seals, Fred. What's next on the program?
I'd like to take a few minutes to cover a few of the tools I classify as especially handy. Many tools aren't absolutely essential, but they are very handy and save a lot of time. Here are a few of them that I consider especially handy. They pretty much speak for themselves. For instance, these special purpose pliers are worth their weight in sweat and frustration. The hose clamp pliers sure take the trouble out of cooling system jobs. Snap ring pliers are almost indispensable. And this one for removing door and window handles on older models is a real lifesaver.
These funny-shaped wrenches are among my favorites. That distributor lock plate stud wrench is great for adjusting timing on some models. The advantages of the starting motor wrench are pretty obvious, and a crowfoot socket is just the ticket for getting onto a tubing flare nut. Here's another useful assortment. A special flywheel turning tool. Grabbing ring gear teeth with your bare hands can be painful. On some jobs, a remote-controlled starter switch is as much help as another man. And of course, that brake shoe return spring tool is the answer to brake jobs.
I think I'm really going to like working in this shop.
I'm sure you will, Bill. Now, what do you have in mind under the heading of unique and indispensable, Fred?
Well, I have quite a few favorites. Let's see. I would classify this rear axle housing spreader as both unique and indispensable. I don't know how you could service a Valiant or Dart without it.
There's also a spreader for use on certain Dodge truck models. But right now, tell Bill how the spreader works.
On Valiants and Darts, the differential side bearings are preloaded by spacers between the carrier housing pedestals and the side bearings. You have to spread the housing to remove or install the differential assembly. This special spreader tool makes an easy job of spreading the carrier housing.
Even more important, by mounting a dial indicator on a stud attached to one side of the carrier and locating the dial indicator follower on the other side, you can measure the exact amount the housing is spread.
Why is that so important?
You shouldn't spread the housing more than about 20 thousandths of an inch. If you were to spread the housing more than that, you might distort the housing. What other unique tool do you have in mind, Fred?
This overrunning clutch tool used on past model torque flight jobs is one we can't do without. This service manual explains how to use it, but I'll give you the highlights. The gauge tool is essential for properly assembling springs and rollers in the overrunning clutch housing. It is absolutely necessary to use this same gauge to allow the assembled clutch to be installed to the overrunning clutch cam. This vital assembly operation is impossible without this gauge.
Maybe that's why we didn't service those torque flight transmissions in the shop I came from.
This past model torque flight tool suggests a good point about special service tools. The older they get, the more you're apt to need them. In other words, older cars are more apt to require major services. That's when some of these tools really earn their keep.
You're absolutely right, Tech. Some of the hardest working tools we have here fit past models only. And you might be surprised, Bill, at how many past model tools also fit the current models. But I better get on with my lecture. I don't want any of my technicians to get into a wrestling match with an engine or a transmission. We have all the necessary work holders, stands, jigs, and fixtures to handle heavy assemblies, including truck components. Our high-lift transmission jack is one of the best investments I ever made in a time-saving safety device. It sure takes the hard work out of handling automatic transmissions. Of course, we have engine stands and rear axle repair stands. I don't think I have to dwell on the merits of that kind of equipment. Besides, I want to get in a few comments on testing and measuring devices before we run out of time. Accurate diagnosis and precision service work wouldn't be possible without good testing and measuring equipment. I'd like to give you a quick rundown on some of the equipment you'll find in this shop to help you do a better job. We sell more and more how to use this rear axle gauge. I'll let you do the work, and I'll bet you a week's pay you'll do a perfect job the first time. On engine tune-up work, you can't do much of a job without a timing light, tachometer, vacuum gauge, and float level gauges for carburetor work. Electrical test equipment becomes more important every year. We couldn't operate without our battery tester, combination voltmeter and ammeter, distributor test stand, and engine analyzer.
Don't forget the alternator. There are millions of alternators in use now, and you can't service them without special test equipment and special service tools. You need the complete set so you can test the rectifiers, replace a slip ring, remove and install rectifiers, and service the end shield bearings.
These pressure gauges are the answer to troubleshooting automatic transmission problems. But like I said in the beginning, Bill, I couldn't begin to cover all of the special tools and equipment we use here in one session. Besides, even if I could cover all of the tools and equipment, you couldn't possibly remember all the details, and I wouldn't want you to try. I'll expect you to use these service manuals. They'll tell you when and how to use these tools better than I could.
There's just one thing I'd like to add to that. Don't ever forget that a good torque wrench is one of the most important tools of the trade. Don't ever take tightness for granted. Torque it to the correct inch or foot-pound specification. Well, the time has come to wrap up this session, fellas. But before we do, I just want to say that you'll pick up plenty of useful ideas in the reference book. So make good use of them, and they'll help you make better use of the tools of the trade.